All right, everybody. Here's a couple of examples I thought you might find interesting. We've discussed vector fields. We talked about definitions and things like this. We said a vector field essentially is a vector value function that assigns a vector to different points in the plane or in space. And we use DESMOS in class also to show some examples of vector fields. I've got one shown right here in this figure. We also mentioned a few special kinds of vector fields. We talked about radial fields, rotational fields, and gradient fields. So I thought you might like to see a couple of examples, introductory examples. Okay, and of course, we'll get more in depth with this as the semester progresses. But anyway, so here's the idea again. So here we have a vector. This is a rotation field. Okay, the vector field is given, its components are y and negative x. Notice that the unit circle is placed within it. Okay. Note also that the field is a rotational field, which we said. Determine if there are any points on the circle at which the vector field is tangent to the circle or normal to the circle. So I think you can see by the figure itself, pretty much solves itself, doesn't it? If you notice the vector fields moving or swirling around the circle itself, you can see that the vectors are pretty well tangent to the circle itself. So in other words, if you were to put some tangent vectors on there, maybe even just unit tangent vectors on there, then the unit tangent vectors would be parallel to the vector field. On the other hand, gang, if you were to put some normal vectors on there, then they would be perpendicular, right? So here's a way to look at it. The equation of the unit circle, if you notice, it has this form. It has the form phi of x and y is equal to a constant. Now remember from our earlier work, and that's the equation or the form of a level curve, right? That's a level curve. Now we know that gradient vectors, we proved it, right? One time for all time, that gradient vectors are orthogonal to level curves. So let's do this. Let's call that phi of x and y. Then the gradient of it we know will always be orthogonal to the level curve. In other words, in this case, that blue circle that you see, the unit circle. Now notice also, right, if we take that gradient and we dot it with the vector field, then we're going to get zero back, right? So this tells us that the vector field is orthogonal to the gradient vector everywhere along that curve. Now, if we put some gradient vectors on there, here's one, for example, right? Maybe we'll put one over here. You could put as many on there as you like, but no matter where you place them, I think you can see visually, right, that the gradient vector is going to be normal or perpendicular to the vector field. All right, so that tells us that the vector field itself will be tangent to the circle, okay, rather than normal to the circle. Pretty interesting solution, I think. Yeah. Now, I have another example here, different vector field. Take a look at this one. Let me see what I do with that one. Here we go. Okay. So this time the vector field is given by y and x. Those are the components, and the unit circle, as before, is dropped in there. This time, again, you'll notice I actually placed some orange vectors on there. Those would be the gradient vectors. Okay, and the blue field itself, right? The blue vectors represent the vector field. And so it's the same question as it was in the last example, right? Are there any points on the circle where the vector field is tangent to the circle or normal to the circle? So looking at the vector field itself, I think we can see that the vector field is going to be tangent to the circle right here, again right here, and then again here. So it looks like it's at the intercepts, doesn't it? Looks like our vector field is going to be tangent to the unit circle at the intercepts. And we can approach the problem the same way that we did before, right? We have the circle x squared plus y squared is equal to 1. And then we refer to that as phi of x and y, right? We said it has the form of a level curve. The gradient, of course, as before, was this. Now notice that the gradient vector dotted with f, right? It'll give us that quantity right there, right? Oh, I got it. Oh, yeah, I got I was thinking that. I thought I had it wrong. Now notice that this quantity will equal 0 at the intercepts, exactly like we said, right? Visually looking at the figure here. Right, because at the intercepts, right, either the x coordinate is 0 or the y coordinate is going to be 0. So at any one of those four locations, this quantity is going to equal 0. So that means at those 4 points, the gradient vector and the force field are going to be orthogonal. Okay. And so we can see that right here, right? That orange vector, that's your gradient. Notice it's orthogonal to the blue field right there. And the same at the other three locations. Now, notice I also carefully placed four other gradient vectors on there, gang. This one at a 45-degree angle, and then here again at 3 pi over 4, 5 pi over 4, and 7 pi over 4. What do you notice about the gradient vectors, those orange vectors, in relation to the blue vectors? Yeah, they look parallel, don't they? They look parallel. At this point, where the angle would be pi over 4, it looks like they are in alignment, perfect alignment right there. Like they're pointing in the same direction. And the same can be said at 3 pi, or I'm sorry, 5 pi over 4 right here. Whereas they're opposed to each other at 3 pi over 4 and 7 pi over. They're still parallel to each other. They're just pointing in opposite directions. Those points, right? So this would be square root of 2 over 2, square root of 2 over 2. This one down here, and then, of course, these two would have opposite signs. Okay, so at those four locations, we know that we see that the gradient should be parallel to the vector field. Now, here's something that we can do, right? We know that the dot product of these two vectors. Now, this is the original definition we came up with in previous class, right? Is equal to this. So now, when the dot product of these two vectors, well, now we found that already. We said that was 4xy. Okay. But again, if I take the magnitude of these two vectors, multiply them together, and then divide both sides by that, I'll leave that to you to verify. You're going to wind up getting this expression. And of course, we can cancel a factor of 2 from the top and the bottom. And we'll have this. Okay. Now, here's what I'm going to do. Let me take the first point at pi over 4. So let me say at the square root of 2 over 2, square root of 2 over 2. If I input that ordered pair into this expression over here, well, here's what we're going to get. All right, so square root of 2 over 2 is going to be what? 2 over 4 times 2, which is a half. Down here, we're going to have a half plus a half, which is equal to 1, which is equal to the cosine of theta. And if that's the case, then that theta is equal to 0. So as we said, right, we looked at the figure and we said, well, all right, well, at that point, the gradient vector and the vector field are in perfect alignment. They point in the same direction. So the angle between them should be 0. And we just verified that with this calculation. Now you can do the same thing by taking the other 3 ordered pairs to verify that at 5 pi over 4, the vectors will be in perfect alignment, so the angle between them will be 0. Just take these coordinates, gang. Take these coordinates and plug them back into this expression right here. Whereas when you plug the other points in, right, at 3 pi over 4 and 5 pi over 4, when you plug the ordered pair, the coordinates of those into this expression, you're going to wind up getting a -1 out. Right here, you're going to have cosine of theta equals -1. You can verify this now, which means that theta is going to equal pi, which means that they are 180 degrees. They're opposite of each other. Okay, and so we found all the locations on our circle where the vector field is either tangent to the curve or orthogonal to the curve.